Hi everybody, this is a walkthrough for linearizing a power function for your IA. We're going to graph the original power function based on some made up data. We'll add error bars, we'll add a trend line. That you probably already have done or know how to do. And then what we'll do is we will manipulate the data in such a way as to plot a linear function so that we can determine the values of the parameters of the power function, and most importantly, the uncertainties in those parameters. The parameters of the power series will be the power function will end up being the slope and y-intercept, or we'll get them from the slope and y-intercept of our linear function. And if we plot a maximum fit and a minimum fit, we will be able to figure out what the uncertainties in those parameters are. Okay, let's start by just making the graph. So I completely made up data here. This is fake data. That means that the trend lines that we add will be basically perfect, and yours won't be, and that's to be expected. But, you know, that's what I did. I have mass data and acceleration data, and we probably already know what relationship should exist, and I'm not sure the result we're going to get from this analysis will be the result we expect, but I figured if I picked something that is similar to what we already know about, that might make it make more sense. So we have some made up data, right? These are mass values and mass uncertainties and acceleration values and acceleration uncertainties. Presumably these uncertainty values are from taking half the range of an average of mass measurements and an average of acceleration measurements. And we're going to make the graph. Let's just do that. So in Excel, I'm going to highlight the mass values. I'm going to hold Control on my keyboard and highlight the acceleration values. Excel expects that when you highlight data to put it on a graph, that the X data is to the left and the Y data is to the right. You don't have to do it this way, but this is the simplest way to do it, so this is what I recommend. If you have to copy and paste your data so that they're in this orientation, you should do that. So we're going to go to Insert, and in the chart section, we're going to do scatter plot, right? And we don't want the ones that connect the dots. We don't connect the dots. We just want the dots. We just want the data points. And we should, oh, hold on 1 minute. I got some good feedback on my first video that maybe we should make this text larger. Let's do that. So people, they said, especially people reading it on mobile would be able to read it. I hope that's better. Let's embiggen that as well. Can we make all the text bigger on there? Let's do that. Okay. So let's add a chart title. This is all the good stuff we would do. This is acceleration versus mass. And we're going to go to the plus sign. Let's add some axis titles. This one is going to be our dependent variable, which I'm calling acceleration, which let's say we've measured it in meters per second squared, because why not? And the x-axis is our independent variable, which is mass. Let's say we've measured this in the regular units of kilograms. And there we have a function. It's, we can see the data, we're going to add a trend line. I think it's clearly not linear. And if we select the data, or really if we just select the graph and hit plus, we can, oh, you know what? Let's add the error bars first. Click error bars. Let's add error bars. And we definitely want to go to this arrow over here and go to more options. Because the error bars they put on by default are using something called standard error. And I'll be honest, I don't remember what standard error is. We don't want standard error. We have the uncertainties. We determine those from our measurements. And those are the uncertainties that we want to include here. So you can see here that automatically the horizontal error bars have been selected. And that's what it says here, horizontal error bar. So let's do that. We want custom. We don't want a fixed value. We don't want a percentage. We don't want to use standard deviation. We want custom, and we have to tell it what values to use. So it allows us, if we want, to use different positive error bars and different negative error bars. So the error bar to the right will be different than the one to the left. And for us, they're the same. It's plus or minus the same amount. Hypothetically, you could have uncertainty where it's plus, one amount or minus another, a different amount. But we don't have to worry about that. So I'm going to select this little button here. and then I'm going to select, since we're doing the horizontal error bars, my mass uncertainties, and Excel knows which one of those goes with which data point. And I'm going to select the same exact data for the negative error bars, and then I'll click OK. Right, and there they are. And you can see they're different sizes now, because for different mass measurements, I got different uncertainties. And now if I select the vertical error bars, I get the vertical error bar options. And if you lose it, you can click these bars here. And again, custom, and we'll specify a value. I want the acceleration uncertainties for both the positive and negative uncertainties. And we'll click OK. And there we have it. Okay. Great. So maybe there's a lot of uncertainty there. It's okay. And now let's add a trend line. So plus, this is where you go to add or remove chart elements. We want to add a trend line. And by default, it does a linear fit. Now, I assume someone could have programmed Excel to automatically give you the best fit, but we have to do it ourselves, which is probably good anyway. So I know that this is a power function. And so I'm going to select that, right? We could probably get a polynomial. I don't know why. The linear function never goes away. I have to select it and then press delete. The polynomial is definitely not good, actually. Logarithmic doesn't look good. Power. Ooh, look at that. Power function looks perfect. And we can go ahead and add... we can select to display the equation on the chart. I'm not going to display the r squared value, because it would basically be 1, because this is made up data that is perfect. So there we have an equation. Y equals 5 times x to the negative 2 power. That's what makes it a power series. Y being proportional to x raised to some power. We probably should change the y and the x to what they represent. So y is acceleration, so we'll call it A. And x is mass, so we'll call it M. And we could probably figure out what the unit has to be on the 5 so that this equation works out. So this is strange. If we have mass raised to the negative 2 power, we would get kilograms to the negative 2 power. If we plug in kilograms and raise it to the negative 2 power, we'll get kilograms to the minus 2. So to get rid of kilograms to the minus 2, the unit here would have to include a kilogram squared. Now, we're not done yet, but it would need to have a kilogram squared to get rid of the kilogram to the minus 2. And if we want to end up with acceleration units, which we know are meters per second squared, we have to incorporate meters per second squared in here. So I'm going to say that this is meters times kilograms squared divided by seconds squared. We could have said seconds to the minus 2. It's a good IB thing. Let's do that. I like that, actually. So we have meter seconds to the minus 2 power, which is what we want to end up with, because we know that the right-hand side should end up being equal to an acceleration. And to get rid of the kilograms to the minus 2 that we're going to get here, we have to multiply by kilograms squared here. And if we want, we could put like an asterisk there, a multiplication symbol. We could do that here too. That's it. That's fine. All right, so there's our function. And we could probably figure out what this represents. We basically have... Oh, what do we have? Well, I don't know. I'm thinking this is related to a force. Newtons, which is the unit for force, as we know, is kilogram times meter per second squared. So this is a kilogram meter per second squared times an additional kilogram. So technically, I guess this is a Newton kilogram, which is nothing, but that's what it would be. I digress a little bit. So here we have a slope. Sorry, not a slope. We have two parameters. We have this coefficient that is being multiplied by m to a power, and then we have the power minus 2. And these parameters come from measured values that we plotted on a graph, and those measured values have uncertainties. And so the calculations that we do with those measured values, the things we calculate using those measured values, should also have uncertainty. So this 5 meters per second squared times kilograms squared is meaningful. Maybe, presumably. And it should have uncertainty. We don't know that this parameter should be exactly 5. It's 5 plus or minus something. And also, we don't necessarily know that the power on the m should be exactly negative 2. That may also have some uncertainty. It should have some uncertainty. But I don't know how to figure out the uncertainties of those parameters using this power series graph. If we can linearize this graph, however, then we are going to be able to figure out one of these parameters with its uncertainty from the slope and the slope uncertainty, and we'll be able to figure out the other parameter and its uncertainty from the y-intercept and the y-intercept uncertainty from the linear function. That's why we are doing what we are doing. I'm going to try to briefly explain what we did, what I explained in the original linearization video. Like what are we going to do next? How are we going to manipulate this data so that we get a linear function? So a power series, a power function is in the form of y equals m. This is different m. This is just what we call it, mx raised to the a power. And let's make this nice and big. Okay, and if we want to manipulate this data so that we end up with a function that is linear in the form y equals mx plus b, what we can do to get that a out of the exponent is we can take the base 10 logarithm of each side. Now, it's been a long time since I really learned a lot about logarithms. I don't know how much you've learned about logarithms, so I can't explain too much in this video, and you might not understand too much from this video, and that's okay. This is a practical application. This is a walkthrough, so do what I'm doing, even if we don't completely understand why. If you're really interested, which is fantastic, go on YouTube and look up logarithms. I'm sure you will find some good videos explaining what logarithms are and how we can use them to manipulate things. So if we take the logarithm of both sides, we'll end up with the following. Log of y equals, when we take the log of m times x raised to the a power, what we get is a times the log of x. That brings the a out of the exponent. And then we'll add the log of m. Like I said, you might kind of just have to take my word for it. I hope you can see, though, that this is basically in the form y equals mx plus b. It's log of y and log of x, but if we take the log of the mass and the log of the acceleration, that's the manipulation we're going to do, and we plot those, they should give us a linear function, and the equation for that linear function will match what I've just typed. And then we'll be able to get the slope and y-intercept and determine the values of a and m and their uncertainties. So let's just keep going along. Replay that a few times if you need to make sure that makes sense. I'm going to select all this data and just move it over a couple columns. We need to make room for our manipulations. I'm going to make this graph smaller. We're basically done with this graph. We don't really need to see it anymore. And let's make that text a lot smaller. Oh, look at that. I clicked one time and it made all the font size perfect. Okay. So this column is going to be log of mass, and this is going to be the log of mass uncertainty. And this is going to be the log of the acceleration. And this is going to be the log of acceleration uncertainty. And we can make these columns the right size. Let's make this bigger like the other ones. I gotta do this again. Okay. So we have to take the base 10 logarithm of the masses, and that's simple to do. Excel will do it for us. We type equals. We type log. It gives us some suggestions. Log 10, log base 10 is an option. I prefer to type it. You can click on it. We can open parentheses, and we could tell it what number we want to take the log base 10 of, and we want to take the log base 10 of the mass. And we can close parentheses and click enter. And we can take this value and we can drag it down, which applies that same equation, log base 10, of the value in column B, and it does all those for us. I'm going to use this decrease the decimal. Actually, yeah, decrease the decimal so that this doesn't look ridiculous. I'm not so worried in this video about going over precision and sig figs. That's something we can discuss another time. You can look at that on your own. I'm just going to make these look kind of manageable. And I guess I'll make them bigger. All right, and let's do the log of the acceleration, because the uncertainties are going to be a pain in the butt a little bit. So this equals log 10, and we want that to be of the value in the column F, so F3 for this one. And then we want to apply that same calculation, take the log base 10 of the value in the F column, and do that for all of these. And we get a bunch of negative values. Logs are weird. So, that is to be expected. And let's decrease the decimal. That looks good. Okay. Should we plot this first, or should we do the uncertainties? Let's do all the data manipulation first. So we don't have a rule on our data booklet for how to propagate uncertainty when we take the log of something. So we're basically just going to say, let's make sure that the percent uncertainty in the log of the mass is the same as the percent uncertainty that we had in the mass itself. And so the equation we'll use here, I'll make this nice and big so we can see it. We're going to say that the delta M divided by M should equal, delta being the uncertainty, equals delta of log M divided by log M. So if we take, I feel like I wrote this backwards. That's okay. So if we do, so we know 4 of these 3 things. We know the uncertainty in the mass. We know the mass. We know the log of M. Sorry, we know the log of M down here. We don't know the uncertainty in the log of M. So if we take the uncertainty in the mass and divide it by the mass, and then multiply by, think of it as cross-multiplying, multiply by the log of M, we'll have the uncertainty in the log of M. All right, so again, play that back if you have to, pause and think about that. But here's how we're going to do it in Excel. So I'm going to say that the uncertainty in the log of the mass is equal to, I'm going to open parentheses. I don't know if we have to, but I am going to. Equals the uncertainty in the mass divided by the mass, close parentheses. That would be essentially the percent uncertainty of the mass. And then we're going to apply that to by multiplying by the log of the mass. And this should give us the uncertainty in the log of the mass. Let's see. Okay, that looks good. It's a smaller number, which is a good start. And we can apply that calculation all the way down. And let's change how many decimal places there are. And let's make the font size bigger. Okay, so those are our uncertainties. And yeah, looks fine to me. And we're going to do the same thing for the uncertainties in the log of the acceleration. I'll try to write this one right. So we're looking for the uncertainty in the log of A, and that over the log of A, right? The percent uncertainty in the log of A should be equal to, not delta, A divided by A. And so again, if we take the uncertainty in the acceleration, let's write it out. If we take the uncertainty in the acceleration and divide it by the acceleration itself, that's the right-hand side of that equation. That's the percent uncertainty in the acceleration. And then we apply that to by multiplying it by the value of the log of A, and that'll apply that same percent uncertainty to this new value. So if there was 10% uncertainty in the acceleration, there will now also be 10% uncertainty in the log of the acceleration. And sure enough, it's a smaller number, which is good. Uncertainty should, typically be smaller than the value itself. Drag that calculation down, and let's change the decimal place a little bit. Uh-oh. Okay. I think I made a big boo-boo. Okay, so I made up my data earlier, and at some point I changed my acceleration values, but I forgot to go back and make up new uncertainty values. So I'm going to pause the recording, and I'm going to make up new acceleration uncertainties, and then we'll get back on track. I didn't notice it from the original data because it only happens a few times. Some of these uncertainties, like this, and a lot of them, are bigger than the values themselves, and that shouldn't be. So I'm going to pause this and to you, I'll be right back. And I'm back. It's like magic. There we go. That makes more sense. Again, this is all made up data. Anyway, you should not be using made up data. Thank you very much. But for this tutorial, I can do what I want. So let's make this font size a little bigger. There we go. We have uncertainties that make more sense considering what they are the uncertainties of. Okay. We're done with math for, just a little bit. What we need to plot now is the log of our y value versus the log of our x value. And so let's select those. The log of our x value is on the left side. The log of our y value is on the right side. That's how Excel wants us to select those. And if we go to Insert and pick an X scatter chart, and we do the one without connecting the lines, there we go. I'm going to make this bigger and cover up the data. We don't really need that data anymore. Let's make this nice and big. Whoa, okay, that's too much. And let's make the font size bigger so we can read it. And, like I said, logs do weird things, so a lot of this is in the fourth quadrant, and that's totally fine. This is not the graph of our data. This is the graph of our data manipulated, right? This is an ends to a mean. Nope. It's a means to an end, folks. A means to an end. So let's, we should label this well, right? We should label this. So let's do that. This is the log of acceleration versus the log of mass. And we should add axis titles. And this title is the log of the acceleration. And this is the log of the mass. And you know what? I honestly don't know what the units would be there. If we have an acceleration and we take the log of it, I don't know what those units are, and I'm not too concerned about it. Am I concerned about it? I'm not that concerned about it. We know what the units are going to be for our parameters. We've already figured that out. We just need to figure out what the uncertainty in those parameters are. Okay, so we have our graph labeled. You're going to show this graph on your IA, so you want to label the axes. Let's go ahead and add error bars. Oh, we do need the data to be visible, so we can add the error bars. Let's shrink this down momentarily, and we'll go to the plus sign, and we'll add error bars, and we're going to do the same thing. We don't want the standard error that they give us by default. Go over here to these bars. For the horizontal error bars, we'll select custom and specify a value. The x-axis is the log of mass, so we will select these log of mass uncertainties for both the positive and negative error values. And then we will select the vertical error bars, and we'll go custom, and we'll specify value, and we want the log of acceleration uncertainties for both of these. Are those negatives going to give us a problem? Let's click OK and find out if my computer explodes. We'll know. No, it worked out just fine. Excel doesn't care if we plug in negatives there. That's great. Great. And finally, okay, let's embiggen this again. Finally, let's add a trend line. It's going to give us linear by default, which we know we want this time. But let's still go in here. We definitely need to do this time. Go to more options, click these bars for the trend line options, and let's display the equation on the chart. Okay, and let's make that a little bigger too. And let's go through this, and let's update this so it matches what this really is. This is the log of acceleration, log of A, let's call it log of A, equals -2 times the log of mass plus 0.0699. What the heck? Well, the -2 looks familiar, right? The -2 was the exponent on this graph, and we have a -2 in here, and that actually makes perfect sense if you think about what we previously explained. And this 0.699 over here, well, let me go back. We start with an equation, a power function, in the form y equals mx raised to the a power. So a for our function is -2. And when we take the log of both sides, the a becomes the number being multiplied by the log of x. So the -2 was our exponent on the m, and now it's the number being multiplied by the log of m. Right? So a was up here, and now a is out front here. That's perfect. And this y-intercept, this plus b over here, we know should be the log of m. Well, we don't really want the log of m. We want m. And that's okay. We're going to be able to figure that out. Just like we can take the mass and then determine what the log of the mass is, we can start with the log of the mass and work backwards to figure out what the mass is. I'm saying mass. Is that right? I'm saying mass because it's m here. This is not necessarily mass. So log of m. If we know the value of m, we could take its log. And if we know the value of the log, we can work backwards and figure out the value of whatever m is. Sorry for the confusion. Okay, enough talking about it. Let's show how we can take that 0.699, which we know is the log of the m in the form of the equation y equals mx raised to the a power, and turn that back into m. And it's pretty simple. We're going to, if we're doing the base 10 logarithm, and so what we're going to do is take the number 10 and raise it to the power 0.699. Right? That's the opposite function of a base 10 logarithm. So if we do that, equals, and we don't have to select a cell for this. We can literally just type numbers in, 10 raised to the 0.699 power, and we get 5.000 and then some numbers, right? And in our equation from over here, it was 5. So that parameter was 5, and we get 5 from the linearized graph when we do 10 raised to the power of 0.699, and the a parameter, which was the m raised to the -2, mass raised to the -2 power, that's right here in front of the log of mass, right? And so those are, those parameters that we got from the equation for the power function are still present in the linearized function. And now we need to figure out what the uncertainties are in them. I'm going to make a little room right here by selecting all this stuff and just, if I do it right, and okay, third time's a charm. If I select all this stuff and just kind of move it behind the graph, it's there. but it's hidden. I'm basically going to do right now what you hopefully saw in the video that I posted from Chris Donner. I think his explanation for how to draw the maximum and minimum fit lines is great, and I'm just going to recreate that here. So all credit goes to him, and hopefully this will make sense. So you can think about, let's go to draw. Each of these data points has vertical and horizontal error bars, and you can almost imagine that there's basically an imaginary box here. And the data point, that last bit wasn't so good. The data point we think is right here, but because of the uncertainty, any coordinate within this box is, would be an acceptable value, is a possible value for this data point, right? Our best understanding is that it's this coordinate right here, but it could be anywhere within this. And because of this range, we could plot different straight lines that go through these imaginary error boxes that fit within the error bars, some that are steeper and some that are less steep, and that's exactly what we want to do. So for the first one, let's do the minimum fit, just because that's what I thought to do. To get the minimum line, the line that fits this data that has the minimum slope, we want to plot a line that goes from the top left corner of the first data point. Nope, that's wrong. Sorry. From the bottom left corner of the first data point. Not a huge difference for this one because of those vertical error bars, but we want to go from the bottom left corner of this first data point to the top right corner of this last data point, right? You can picture that uncertainty box there. And if we do that, this line is, I'm going to draw a really bad line. This line looks like that, something like that, right? And that's a line that is less steep than our best fit, which is the trend line that Excel gave us. And so what we need to do is we need to figure out what are the coordinates of this point here, and what are the coordinates of this point here, and then we need to tell Excel to plot a line through those points. So let's start with this first point here. This first point is to the left of the data point. The x coordinate is to the left of the data point. So that's going to be the x coordinate of the data point minus the uncertainty in that value. And it's also below the y coordinate of this data point is below the y coordinate of this data point. And so the y coordinate of this data point is going to be y minus the uncertainty in y. Right? It's lower than y by the amount that is the uncertainty, and it's to the left of x by an amount that is the uncertainty in x. And then when we come down here, it's kind of the opposite. It's to the right of, right, this data point here, this coordinate here, I should say, is to the right of the data point. It's the x coordinate of this data point plus the uncertainty. And the y value of this coordinate is above our data point. So this is going to be y plus the uncertainty in the y. And so we just need to determine what these values are, and then have Excel plot a point through those. And so here's how we're going to do that. So let's put a place to put this data. So the minimum fit is going to go through let's do x and let's do y. The x coordinate is going to be equal to the x coordinate of this first data point, which is the log of mass, and it's going to be that minus the uncertainty. It's a little bit less than that. And the y coordinate will be equal to the y coordinate of that first data point, which is the log of the acceleration, and because it's to the left, to the underneath that, minus the uncertainty in that value. Okay, we don't need all those decimal places. Let's change that. Okay, and we'll do the same thing. This is the first point, let's say. Let's say this is the first point. Let's use the word first, and this is the last. And so this last point has an x-coordinate that is equal to the x-coordinate of the final log of mass plus the uncertainty, because it is to the right. And, we're going to have to resize our graph here. Can we do that with the drawing that's there? Ooh, this might be an issue. Let's see. The final data point is the y-coordinate of the final data point plus, because it is above, the uncertainty in that data point. Oh, it worked. And enter. And again, we can make this more reasonable. Okay, let's make this graph bigger and see if we can get it to line back up again. It doesn't really have to. I guess I want it to. That's fine with me. Okay. Let's plot that first, and then we'll do the maximum fit. So it's pretty simple. I want to basically plot 2 additional data points on this graph and then draw a trend line through them. So if but here's the thing. I don't want to make a new graph. I want to add these data points to the graph that we already have. So I have the graph selected. There's 2 ways I could do this. I can go to chart design and then click on select data, or in the graph, I can right click and choose select data. Either way, we want to select data. And we already have one series of data here. That's, what we've already plotted. We want to add a series. And we can call this min. This is min. And the x values are going to be these 2 x coordinates, and the y values are going to be these 2 y coordinates. And let's click OK. And let's click OK again. Okay, another issue. You guys are recording this live. It's not live when you're watching it, but I'm recording this live, and I realize now that because I let those uncertainties be negative, that instead of this final data point being up here, it's down here because it is a negative uncertainty. So let's fix that. So here's what you would have to do if you had a situation like that. We want, the log of acceleration can absolutely be a negative value. It should be a negative value, but these uncertainties, we want them to be positive. So let's make sure they're positive. The way you can make sure that a value you get is positive, whether or not the math gives you a positive number, is by taking the absolute value. So back when we did this equation, we did a couple of, we did the percent uncertainty of the percent uncertainty of the acceleration multiplied by the value of the log of the acceleration. We're just going to edit this. We're going to put the absolute value in front, equals ABS for absolute value, open parentheses, and then we'll put a closed parentheses at the end, enter. It's not going to change that first number. It was already positive. If we apply that equation to these other cells, they'll all just change to positive values. And the value here changed because we're adding a positive value instead of adding a negative value. And now you can see that new data point is in the upper right corner where it's supposed to be. I'm going to delete that drawing in a second. Anyway, there we go. We can barely see the data points. They are right underneath where we drew them. Let's get rid of what I drew. Go to drawing. You're not going to do this. I know I'm narrating this. I'm just going to get rid of it for you. And delete. Okay. So if we add a trend line through these 2 data points, that will be the line with the smallest slope that fits within the error bars of our data. Let's just do it. And we're going to right click, and we're going to add trend line, and it's definitely linear, and we definitely want to display the equation on the chart. And we want to move it someplace where we can see it. I don't know why they give it to us like that. Make it a little bigger maybe. And I don't particularly care to change this y to log a and that x to log m, because what we really just want is this, this slope value and this y-intercept value. And that's what's going to be useful to us. What I think we should do to make this clear is say that this is the minimum fit line. Let's say that this is the best fit line. And when we do the maximum fit line, we'll label that as well. So we already see that the slope that we got for our best fit is -2, but a slope of -1.2125 also fits within the data, right? And so, we can already see that there's some uncertainty here. We're going to do the same thing to get the maximum fit line. I'll write it out. I'll write out what I'm doing. Obviously, feel free to skip around if you feel like you know how to do this already. But here we go. I'm going to draw it again. I think writing it out can be useful. I don't know. We can stick with red, right? We don't have to change the color. So to get the steepest line, we want to go from the top right corner of this first data point to the bottom left corner of this last data point. And that's going to give us a pretty steep line, right? And this coordinate here, it is to the right of the x and it is above the y. So in both cases, it is going to be x plus the uncertainty in x, and it's going to be y plus the uncertainty in y. It's the opposite of this other corner over here. And then down here, it's below the y coordinate. It's to the left of the x coordinate. This is going to be x minus the uncertainty in x, comma, y minus the uncertainty in y. I guess I should pause and say that hypothetically, you could not hypothetically, I mean, you could definitely have a power function where the power of x is a positive value. And so when you do this linearization, you'll get a slope, a line with a positive slope. And the way that I'm calculating these, the way that I'm figuring out these coordinates for the maximum and minimum fit lines might not be exactly the same way you do it. If we had a positive slope, we would be going, through different corners of the imaginary error boxes. So you have to actually take some care to make sure. Maybe you should do what I'm doing. Maybe you should either print it out or sketch it on paper and figure out, if this is the corner we're going through, is the x coordinate plus or minus the uncertainty, and is the y coordinate plus or minus. If you just blindly do what I'm doing, and your graph is a little different than mine, you might not get the right result. So now let's tell Excel to do that. Let's do the math there. So maximum fit, and we're going to have x's, and we're going to have y's, and we're going to have the first point, and we're going to have the last point. The first point is going to be equal to the x value of this first point plus the uncertainty. And the y value is going to be equal to the y value of that first data point, the log of acceleration, plus its uncertainty. And the x value of the last point will be equal to the x value of the last point minus its uncertainty. And the y value will be equal to, we got to move this graph out of the way, equal to the y value of the last point minus the y value. I guess I stopped typing the equation, and so it messed up. So let's try again. This is going to be equal to the y value of the last data point minus its uncertain. Okay, I'm clicking on that text. This is dumb. Is that what it's supposed to be? Let's double check this one more time. Equals the y value of the last data point minus its uncertainty. There we go. And we can go ahead and make these smaller, less precise, more reasonable. We can resize that, and we can resize that. There we go. I'm happy with that. Okay. Let's plot those data points. We want to add another series. We can right click and go to select data, or we can go to chart design and select data. And we're going to add a series. Let's call it max. This is the maximum slope. It's negative, but it's still a maximum. It's still the steepest. And the x values will be these x values, and the y values will be these y values. And we'll click OK and OK. And you can't really see them, but there's some data points under there. Let's get rid of this drawing. Let's lasso that, delete it. Boom. Gray data point there, gray data point there. If I select them, can I select them? Oh, man. Oh, man. Oh, I got to go back to the select tool. It's late. Select that, right click, add trend line. It's linear. Display the equation. There we have it. Let's make it a little bigger. Again, I don't particularly care about changing the y and x. I'm just trying to get the slope and the y-intercept here. This is the maximum. And there we go. All right, we're almost there. So we know that the slope of this linearized graph is -2, but it could be as low as -1.2. It could be as high as -3.1. We're going to use that to figure out the uncertainty. We also know that the y-intercept of our best fit line is positive 0.699, but it could be as low as 0.3893, or it could be as high as 1.2036. Again, there's way too much precision in some of these. That's not the focus of this video. That's something that you can take a look at yourself, and I can give you some advice if you need it later on. So let's use this to figure out the uncertainty in our slope and y-intercept from our linearized graph. Remember that the slope value is the power that x is being raised to, and the y-intercept is the number that is being multiplied by x raised to a power. What we called M and capital A, which is, I realize now, confusing, or I've realized it since we've been doing this, because I made up data that was mass and acceleration. That was not very smart. It happens. Okay, so let's do the slope first. That one's going to be easier. Okay, so the slope, let's write this out. Let's write out the max. Let's write out the min. Let's write out the best. And let's do this for slope. And let's do this for y-intercept. The maximum value of the slope. I'm going with what is the steepest. It doesn't really matter. I'm going to say that -3.1454 is the greatest slope. I know it's the most negative, but that's physics for you. And the minimum slope is -1.2125, and the best is -2. And for the y-intercept, the lowest y-intercept is 0.3893. Oops. We did max first. Okay. The maximum is 1.2036. The minimum is 0.3893. And the y-intercept of our best fit is 0.699. Okay. So the uncertainties in these things, we're going to do it just like we would do an average. It's half the range. So if we take the maximum value and subtract the minimum value, and then divide by 2, the uncertainty is, wow, the uncertainty is almost 1, almost -1. That's not great. But again, this is all made up data, made up numbers, made up uncertainties. And same thing here. The uncertainty in the y-intercept is the difference between the range. So the maximum minus the minimum divided by 2. Divided by 2. And the uncertainty in the y-intercept is plus or minus 0.4. Again, a very big uncertainty. So be it. It's made up. For the slope, we're basically done because the slope value, I'm going to make this graph a little bit smaller now that we've kind of used it for what we need. The slope value is the power of x. Okay, it doesn't like that. It's the power of x. And that's already it. So the power of x is -2 plus or minus 0.96645, whatever. So we have to, we'd have to determine what precision to use for that -2. If it's -2.00, we could say that it's plus or minus 0.97. If it's -2 or -2.0, we'd have to say that the uncertainty is -1 or -1.0. Close enough. For the y-intercept, sorry for the long pause there. For the y-intercept, this is the log of m. So m is the number that is being multiplied by x raised to the power. And I don't really want to know what the log of m is. I want to know what m is. Well, we've already seen that we can take 10 and raise it to the power 0.699 to get our 5 back. And so if we take this 0.40715 and raise it to, take 10 and raise it to this power, 0.40715, then we will know the uncertainty, we will know the value of m and the uncertainty in m. Right now we know the log of m and the uncertainty in the log of m. Okay, pause. I think I just described something that is incorrect. I think I said we would take 10 and raise it to this power to determine the uncertainty in the value of this m out front. We won't do that, right? We will do a percent uncertainty, right? This 0.4 is some percentage of the 0.699, and we will make sure that the uncertainty in the value of m, which is 10 raised to this power, is the same percent uncertainty. So let's write that out. So 10 raised to the 0.699. So m equals 10 raised to this power. And if we do that, equals 10 raised to this power, we get 5. We saw that before. We get our 5 back. Right? So now let's figure out what the uncertainty in that is. So the uncertainty of this is going to be the percent uncertainty of the log of m, which is the uncertainty divided by the value. And then we are going to multiply that by our value here, right? So this is, 0.4 is some percent of 0.699, and we want to apply that same percent to our value of m. It's a huge uncertainty. Wow. 5.0 plus or minus 2.9. So be it. That's fine. What can we summarize here? We're done. It might not seem like it. We've been doing a whole lot of crazy stuff. I've been recording for almost an hour. Actually, the recording is almost an hour long. I've been recording for longer than that. There's a lot here. This is a lot of work, guys. Here's what we can say. Let's summarize. Let's go back to this graph here. Let's bring that to the front. All right, this is the graph of our dependent variable versus our independent variable. And this is the equation that we were given from Excel for the best fit line, right? When we linearize the graph, right, we were able to, in this case, we were able to confirm that 5 is that coefficient m, and -2, oh, this should be, should be raised to the -2. And the exponent on the x, or the exponent on mass, is -2. We've confirmed these, but we also know the uncertainties in these things, right? So the end of our analysis section should probably be, we'll have our graph of acceleration versus mass. We'll show our graph of the log of acceleration versus the log of mass. We'll show our linearized graph. We'll have our minimum fit line, our maximum fit line. Maybe we'll have the equations for those things shown. And that will all explain how we were able to find these uncertainties, right? Our exponent, a power of x is -2 plus or minus 1, basically. And the 5 out front is plus or minus 2.9. So we'll be able to end the analysis section by saying, our research question here is hypothetically, what is the relationship between the acceleration of an object and the object's mass? And this is our answer. Well, this equation shows the relationship between the acceleration of an object and the object's mass. It's this formula. Not only do we know what formula relates our two variables, we also know that it's not exactly this, or we don't know for sure that it's exactly this. We know that the number being multiplied by, or multiplying the m to the -2 power, we think it's 5, but it could be bigger or smaller by 2.9. It could be as big as 7.9 or as small as 2.1, right? And we would say that. I'm not going to add that to the equation, but I would write that in some text, right? So we would be able to say that the equation that relates acceleration and mass is this formula right here. And we would be able to say that the uncertainty in this coefficient is plus or minus 0.97 or plus or minus 1, depending on precision. Nope. I said the wrong thing. The uncertainty in this this coefficient out front, the 5, is plus or minus 2.9. And we could say that the uncertainty in this power here is, well, we think the power is -2, but it's plus or minus 1, plus or minus -1. And then the beginning of our evaluation section should be some discussion of the significance of this equation, some discussion of the uncertainty, right? This might lead to a conversation about strengths or weaknesses. This was made up data, made up uncertainties, but, that's a pretty big uncertainty, 5 plus or minus 2.9, and -2 plus or minus 1, plus or minus -1. So we might say, there's a weakness here because our uncertainties are very large. We might speculate as to what caused our very large uncertainties, and how we could improve that. Or maybe you'll have very small uncertainties, very small percent uncertainties, and you can talk about that as a strength, and you can try to explain why you think that strength exists. What did you do? How did you take measurements that were so precise, and how did those precise measurements, propagate through all of this analysis and give you a result, an equation relating your dependent and independent variables with very small uncertainties for their parameters. That's it. This is almost an hour long. I hope it's helpful. I would really appreciate your feedback. Please, honestly, give me feedback. Comment on the YouTube video, or if you're one of my students and I'll see you in class, tell me in class that this was helpful, or honestly, tell me if it was not helpful. As long as your criticisms are constructive and polite, I actually really appreciate them. That's it. I'm going to bed. Good luck linearizing your power function for your physics IA.